So now for example number 5, we're going to determine the altitude from an atmospheric pressure. And so they said find the altitude above sea level which the atmospheric pressure is 4 pounds per inch. And they don't, the textbook doesn't give you a bunch of information, but they do tell you the model that you could use. So they have this model here. So this is example number 5 out of your textbook. They have this model of 7.35 is equal to 14.7 times the quantity, 0.5, and it's 0.36 divided by 0.36, all right? And you got to read in the fine print, this model represents the pressure at 3.6 miles above sea level, okay? This is supposed to be an ant symbol, but somehow it got jumbled up here. At 3.6 miles, okay? And so what they did is they said, well, all right, let's mathematically double that. So they said, all right, so if I say 14.7 and then 0.5, and if I double that number, we'll get a different answer. So let's break this down before we go any further. Your textbook doesn't break it down, but I want you guys to understand what we have here. What do we have here? Well, what they did is they just went out and measured a few things, okay? Now the way that this model works is 14.7 is an initial condition, right? So this is our initial condition, so that will never change. This 0.5 is like our rate or base, which is the same as 1/2. So it seems like every 3.6 miles that you go up, it seems like the pressure would decrease by exactly 1/2, right? And so that's exactly what happens. So here, when I double my rate, it will be exactly 1/2 of 7.35. Okay? And what they really wanted us to know or find out was, when will this equal 4 pounds per inch? So the question that the textbook says is, when will the atmospheric pressure, or really we should say where, how high above sea level, is it inches squared? Yeah. Yeah, that's the unit. Pounds per square inch. Okay? So if you were just to read the textbook, this might be a little confusing. That's why Mr. Adams goes over it with you. So this model, the initial condition at sea level must mean that it must be about, so let's just start listing the information we know and then we'll go from there. This right here, this information right here means that at sea level, the initial condition, when T equals 0, at sea level, the pressure is 14.7 pounds per square inch. Okay? That's what that means. And every 3.6 miles that you go up above sea level, your pressure decreases by 1/2. Does that make sense? So once you're 3.6 miles up, you get exactly 1/2 of 14.7, which is 7.35. You guys with me so far? So now if you go twice that amount, 7.2 miles up, then you get exactly 1/2 of the 1/2, which is 3.65. So this is just like the population model we just did. And what we're interested in is when will it be 4 pounds per square inch? So it's going to be somewhere in between, right? It's going to be somewhere between 7.2 miles and 3.6. That's our common sense check. So if I do a bunch of math, okay, and then the answer I get is like 30, then it's wrong. Somewhere I made a mistake. Does that make sense to you guys? Just kind of nod your head if it does. And if it doesn't make sense, go like this. Okay, nod heads, let me see. Somebody's doing this, that's funny. All right, so that's okay. All right, so now what we're going to do is our model then would be is that the atmospheric pressure, P of T, or in this case, they said P of H because we're talking about the height, is equal to 14.7 times 0.5 raised to the H all over 3.6. And what we want is to figure out when this will equal our P of H. When will this equal 4? So essentially what we're going to do is we're going to solve this way. Now in the last example I showed you how to solve this by hand using natural log, right? Now let's skip that and do a shortcut, quick way on our calculator. So let's assume you're taking your ACT exam, it's a time test, you got about a minute per question. There's an easy way to do this. Who remembers the easy way to solve that equation? By graphing. Well, the easy way is to graph the left-hand side of the equal sign and then graph the right-hand side of the equal sign. Now, when I do that, I may need to adjust my window. What did we say H should be between? 3.6 and 7.2. And so, what do I want to do next? How do I find the answer to this? Yes? Find where they intersect, right? So what I'm going to do is I'm going to hit second calc, and I'm going to come down to option number 5, which is find the intersection. I'm going to take the first curve and use the cursor to get as close as I can to where they intersect. Hit enter, it'll say second curve, hit enter again, guess. 6.76 is what it looks like, right? So, by using my calculator, it said that 6.76 is approximately what H would be. Okay? Of course, on the calculator we set X. Hey, you know what? That's exactly what the book says. Not too shabby. Is there another way we could have done this on the calculator? We've figured out a lot of ways to get the answer. Is there another way we could get the answer? Somebody said it earlier. Somebody said it back here in the corner earlier. What's another way we could get the answer using this information? How can we double check? That's what we're going to do. We want to double check that. The calculator's given us an answer, but again, Mr. Adams could have entered something in wrong. What if I entered one number in wrong when I went to graph it? How could I double check this? See, I've got this equation here, and I said that h solves the equation, this equation here. How can I verify that on my calculator? Well, one way that I could do that is I could plug in my value for h and see if it works. So I could say 14.7 times 0.5 raised to the 6.76. Oh, I got to put that in parentheses. 6.76, whoops, not quite done yet, divided by 3.6. Now when I hit enter, what should the answer spit out? What should the calculator give me for an answer? It should be 4, right? If I did my work. Now will it be exactly 4? Why? Because I rounded, right? Because the calculator rounded it a little bit. So it's 3.9999, whatever. Okay? Any questions? No?